Hi friends, welcome back to the Introduction to Material Science and Engineering course offered by EdupediaWorld. Previous couple of lectures we started discussing about crystal structures, and the last lecture was specifically about three crystal structure: body centered cubic, face centered cubic and hexagonal. Those were three type of Bravais lattice which falls under the different crystal structures. A point to note is that till now all the discussion which we had was for atoms of a single type, that is we were dealing with one element scenarios like metals which had same sized atoms distributed throughout. We used to discuss the crystal structure for those kind of scenario, but that is not the only kind of possible case. There are cases where there are multiple atoms coexisting, like in the case of ceramics. So is there any definitive pattern and if there is a definitive pattern, are those patterns can they be categorized into certain classes? Can they be classified? This discussion is exactly about that. We'll see the different kind of ceramic crystal system. Okay, so to begin with, let us see the fundamentals about ceramic crystal system. As I said that for a ceramic crystal system there have to be at least two different types of atom, right? Because one type of atom means it is a element and it will fall under one of the 14 Bravais lattices, right? So there need to be two types of atoms for a ceramic to exist. Now the two type of atoms, we confine our discussion for the time being considering there are just two different type of atom, not more than two. So given there are two different type of atom, there will be a difference in electronegativity between the two kind of atom. They may be quite close in electronegativity, they might be very further away in electronegativity from one to another, right? And depending on how different is the electronegativity for the concerned atoms, the nature of the bonding which will exist between the atoms will be either ionic or covalent, or it can be a mixed intermediate between ionic and covalent nature, right? So when will be the system, when will the bonding be highly ionic? It will be highly ionic when the electronegativity difference between the two concerned atoms is quite large. On the other extreme, it will be covalent when the electronegativity difference is quite small, obviously, and mixed is for the intermediate cases. Now here I have mentioned two simple examples which are kind of extreme ends of the spectrum. Calcium fluoride CaF2 has 89% ionic characteristic, whereas zinc sulfide or zinc blend has only 18% ionic characteristic, which means that zinc blend or zinc and sulfur has quite close electronegativity values, whereas calcium and fluorine are quite far apart in electronegativity. Thereby they have ionic nature for the bond formed, right? Now that we know that it can be either ionic or covalent, in case the atoms concerned are of the ionic nature, that is they are separated with a large difference in electron, then what we can consider is that instead of considering two different kind of atoms, we can consider them as ions, right? Like the one which will be electropositive will be acting as the cation, whereas the one which will be electronegative will act as the anion. For example, in our calcium fluoride case, what I can do is I can take Ca2 plus as the cation and F minus as the anion, right? So this can be now translated into an ionic system rather than independent atoms, and this helps us visualize the thing that there is a attraction existing between them due to the ionic nature. Now that we see that there is a coexistence of cation and anion, this brings into picture the concept of charges, right? Obviously their cation will have a positive charge, anion will have a negative charge, but as such the whole crystal system cannot remain charged. It has to be electrically neutral. Therefore one bottom line or one important criteria for the crystal system to be sustainable is that the charge given by the cation should counteract the charge given by the anion. Okay, that's what is presented here. Characters affecting crystals, specifically what it means is that depending on what characteristic will the crystal structure vary. So though the two important characteristics which defines the basic crystal structure that we'll get are, one is that it needs to be electrically neutral, and the second is the cation to anion size ratio or radius ratio. Let me explain briefly both of them. What do I mean by electrically neutral? As I said that since it has to be electric neutral, but how does this affect the crystal structure? Like the example over here, if we have calcium 2 plus and fluorine 2 minus, what this means is that for charge neutrality to be maintained, there has to be a single calcium 2 plus, and against each single calcium 2 plus there has to be 2 fluorine minus, right? There has to be a ratio of 1:2 between calcium and fluorine for the electrical neutrality to be maintained. This is how the crystal structure is being affected by electrical neutrality, the maintenance of electrical neutrality. That is, this ratio has to be maintained. Similarly, if we take another example, let's say cesium fluoride, CSCl. Now here we have CS plus and Cl minus. Since the charge is only plus and minus, the ratio remains 1:1, whereas here the ratio becomes 1:2. Okay, so you get the point which I am trying to make. Second, cation to anion size ratio. What do I mean by this? The size of cation, if you come to think about it, cation is formed by losing electrons. Anion is formed by gaining electron, right? Thereby, cation normally will have a size smaller than anion, because on losing electron, it loses its outer shell and its size becomes smaller. Anion, on the other hand, does not lose the outer shell, rather it is gaining the electron, thereby it further enhances in size due to further repulsion created between the neutrons. So the cation to anion ratio, size ratio, kind of determines what will be the crystal structure. We'll see this in more details in the next slide. There you will get much more clarity about what I'm trying to talk. But the point to take home here is that the cation and anion have different sizes, and the specific ratio of a given combination will define how the crystal structure will behave. And why is it so? Let's see. The opposite charges, that is cation, likes to have maximum number of anions surrounding it, and anion likes to have maximum number of cations surrounding it, right? Now if there is a large difference in size between the cation and anion, suppose that the cation is very small compared to the anion, then it can be difficult to accommodate a lot of anions surrounding the cation. Whereas if the cation is of larger size, more number of anions can surround the cation. Thereby the size ratio actually affects the crystal structure. Also, the coordination number depends on the size ratio. How come? Because the coordination number is nothing but how many pieces or different atoms are surrounding a given atom. Okay, so more is the size ratio, that is let's put it this way, smaller is the cation size, less will be its coordination number, because lesser number of anions can surround it. More the cation size, more will be the number of anions surrounding it, thereby more will be the coordination number. Okay, so here I have given you a picture about the idea of cation to anion size ratio and how it influences the crystal structure. Next couple of slides, once we'll talk about what is the stable configuration for cation to anion size ratio under which a ceramic crystal structure can exist, and second, what are the different ranges of cation to anion size ratio and correspondingly the different crystal structure. Let's see first for the stability. Okay, so here we see three scenarios. I have put three different anions which are hollow circles, and the green circle over here is a cation. And as we can see, cation is smaller than the anion. Now for the three different anions, in this case, in the first case, the cation is touching all the three anions. In the second case also, the cation is touching all the three anions, but it is kind of the limiting case. If the cation was even a little smaller, then it would not touch all the three simultaneously. Whereas in this case, in the third case, what we see is that the cation is in fact smaller than the minimum size which is required for it to touch all the three anions. Now you'll say, what is so important about this size? The importance is that for the stability of the configuration, the cation needs to touch all the atoms surrounding it, or all the anions surrounding it. Therefore, this and this structure are stable, and this is the limiting case. This is the limiting case. Whereas this structure is unstable, because the cation is not in contact with all the surrounding anions. It may be in contact with this too, right? If this was somewhere here, then this cation would have been contacted with this and this, but it still would not have been in contact with the third one. Thereby this contract that the cations should be in contact with all the surrounding anions would not be valid in this case. So this is the fundamental. You need to remember this. For stability, the cations should be in contact with all the surrounding anions. Okay, now let's see the size ratio which I was talking about. RC by RA, this is the radius of cation, and this is the radius of anion, and its relation with the geometry. So as I said that normally the cation will be smaller than the anion. Therefore, RC upon RA will normally be less than 1. Okay, so let us see the different cases for RC by RA less than 1. And mind you, this coordination number which we have generated here for different cation to anion ratio and the corresponding coordination geometry, all this can be mathematically derived using geometry. This has nothing to do with metallurgy or material science. This is basic geometrical calculations, but I will not go into details. I will give you the output of the different ratios. The ratio, if the ratio of cation to anion is less than 0.155, then what we'll have is a coordination number of 2, and the coordination geometry will be linear. Let me show how it will be. What will happen is the anion will be 2 small particles, okay, and the cation, as I said, is less than 0.155 times the radius of the anion. So the cation will be basically very small, something like this, okay, and it is touching the first and the second, both anions, and this configuration is linear. It is a linear pattern. So the coordination number is 2 and the coordination geometry is linear. Okay, the second configuration will be when the cation to anion ratio is between 0.155 and 0.225. Then the coordination number will be 3 and the geometry will be triangular planar. Triangular planar with coordination number 3 is the same as this one. Here you see that there are 3 anions, and this is my cation, which is lying exactly at the center. So it is touching 3 anions, and its geometry, as you can see, is in the plane of the paper, right? This is the plane of the paper, and it is triangular. So it is called triangular planar. Okay, if the ratio is between ratio of cation radius to anion radius is between 0.225 to 0.0414, then what we'll have is known as tetrahedral scenario. Okay, Now what is tetrahedral scenario? In tetrahedral scenario, what you will have, this no longer remains a 2D configuration, this now becomes a 3D configuration. So I'll try to give an idea how this will look like, but it might not turn out to be very good representation. Okay, so these three atoms will kind of lie in one single plane. This is my cation. Okay, these are the anions, and a fourth anion will be lying on top here, that is, it is in outside the plane of the paper, right? These three are in the plane of the paper, and this both the anion and the cation are outside the plane of the paper. Alternatively, you can think of it something like this, So one atom, one anion is here, one anion is here, one anion is here, and fourth anion is here, and there is, these anions will be touching each other. Obviously I cannot show you here, but they will be large enough to touching each other, and in between there will be a gap here which will be known as the tetrahedral void, and in that tetrahedral void we'll have the cation placed. Okay, so this is, as you can see, a 3D configuration, and this we have 4 coordination number because this atom, this cation will have 4 atoms surrounding it, 1 2 3 4, and the geometry is called tetrahedral geometry. Okay, now if the radius ratio between the cation and the anion is between 0.414 and 0.372, then what we'll have is known as a octahedral geometry with a coordination number of 6, which means that the cation will be surrounded by 6 anions. Now how will this look like? How will the octahedral void look like? So what will happen is, in the plane of the paper we'll have like 4 atoms, right? 4 anions. Then one anion will be within the plane of the paper, it is inside, it is not in this plane, it is inside, and over here will be my anion, rather cation placed. So this 1 2 3 4 anions, this is the 5th anion inside the plane of the paper, this is my cation, and there will be a 6th anion on top of the plane of the paper. So basically what we are seeing here is something like this, okay. So 1 2 3 4, these 4 are these 4 anions at the plane of the paper. One anion will be at below the plane of the paper, one anion will be, this passes through the center at the top of the plane of the paper, and between over here there will be a void, this will be filled by the cation. So now what will happen is, and this cation will be touching all the 6 anions. So we have 1 2 3 4 5 and 6 coordination number, and this is known as my octahedral geometry. Okay, why octahedral? Because it sounds like there are 6 atoms surrounding it, but octa means 8. So the reason is, if you kind of draw the structure like this, so 1 phase, 2 phase, 3 phase, 4 phase, and similarly 4 phases at the bottom. So there are 8 phases within which the cation is confined inside. Okay, so now you have got idea about what is the octahedral geometry. Finally, if the radius ratio between the cation and the anion lies between 0.732 and 1, then we will have what is known as the cubic geometry, and the coordination number will be 8. And as you can think with the name cubic, what will happen, similar to our crystal structure for the metals or for metal elements, what will happen is that the anions will be at the 8 corners, right? 1 2 3 4 5 6 7 8, and there will be a void over here inside, and that void will be filled by the cation, and this void is known as the cubic void, and this whole geometry is the cubic geometry. But remember, this is not equal to body centered cubic. This might appear like body centered cubic, but this is not body centered cubic. Why not? Because for body centered cubic, the atom at the body center should be the same atom which are at the corners. Here the central atom is a different atom, it is the cation. These are the anions. Okay, so this lecture gave you a glimpse into the idea behind the crystal structure for more than one type of atom. We saw the properties, we saw how the geometry is influenced, we saw the influence of radius ratio and the different type of coordination geometry that can exist for different radius ratio. In case the radius ratio is more than 1, which can happen actually, because there is no hard and fast rule that all cations which exist are always less than all anions which exist. So there can be cases where the cation is larger than anion, that is Rc by Ra is more than 1. In that case, the coordination number will turn out to be 12. I am not going to go into further details about it. This slide over here is quite important. The previous slide about stability is quite important. Okay, so with this background, next lecture we will see into some examples of specific ceramic crystal structures, and that will also bring into use the information and the knowledge we gained in today's lecture. So hopefully you will be here for the next lecture. Till then, have a great day. Goodbye.